Welcome back to another episode of Learning Integration, where this lesson will be focusing on integration by parts, Leibniz's notation, and we're focusing mainly on the trigonometric side of things, so sin x, cos x, tan x, those sorts of things we'll be looking to find the integral of. Okay, so this is different from Lagrange's notation, obviously, because it's Leibniz's notation, but Lagrange's way you'll see the most because his is the fx and gx and it's most common, but sometimes you'll come across this. I remember people in some of my classes used to have problems. They liked doing it this way and they had problems going to the other way just because it worked better in their head with this way. I preferred the other way, obviously. I preferred the other way, but I'm going to show you this way because it's the exact same thing. It's just using U's and V's instead of F's and G's. So, on that note, we'll get into it. Okay, let's start with an example. Let's say we got x or y, dy dx equals dy dx equals x sec squared x. Okay, so the reason I put this here is because when you're using Leibniz's notation, let's say I integrate, I find the antiderivative or the integral, it turns to y, because this is a derivative and this is the original, so I'm reversing it. I'm going from the derivative back to the original. I'm anti-differentiating it. And because, unless you want to make it a capital Y, going from a derivative back to the normal function is still an integral. So that's what I'm doing. I'm finding the integral of one side, and I'm finding the integral of the other. Okay. Now that we have that, we can make a comparison. We can assume that this looks very similar to this. In order to do this, to follow integration by parts, we need to assume that one of these needs to be derived and one of these needs to be anti-derived. Just like here, we need to derive u to get u dash, because we need to find u dash here in order to complete this, and we need to find v, so we need to be able to find the integral of this. So don't get too confused, but think of it, we need one of these, we need to find the integral, and one of these we need to find the derivative. So we got to think of it like this. We need to find one, the derivative, and we need to find the integral of another. The question is, how do you choose? Well, let's start easy by labeling it. We need a u, we need a u dash, we need a v, and we need a v dash. Let's say, for argument's sake, we put x as u, and we put sec squared x as v dash. Now, just remember that we're thinking of this as being that. So we're thinking of a u and a v dash. So we got to pick one as u and one as v dash, just to hopefully get rid of any confusion. So we've got our u, we've got our v dash. Now, if we derive u, which is x, we get 1. And if we find the integral of sec squared, we get tan. Because if we derive tan, we get sec squared. So the integral of sec squared is tan x. Now, why did I pick u to be x and v dash to be sec squared? Well, if we put sec squared up here and we had to derive it, we would get something along the lines of the natural log of tan sec sine something or other. But if we derive x, we get 1. Now if you have a look at the formula, we have a u dash multiplied by a v. Now it doesn't matter what v is for the meantime, but we have a u dash multiplied by something. So if we can find a way to get u dash to be 1, then that works out, because when we're doing the equations or when we're working something out, this will be 1. So when we have 1 times this, it'll just be v. Therefore, we have less to work with and less to worry about. That's why I picked x there, because it becomes 1 when it's derived. Or it simplifies much easier than this would if I were to derive it. That's actually a good way of saying it. Whichever one of these simplifies better than the other one becomes u. So x simplifies better than sec squared does, so I picked x to be u. Try and remember something along those lines. So now we have our, I'll rearrange these. We have our u, we have our u dash, our v and our v dash. We have our equation. All we need to do now is put them together. Okay, so if I rewrite this as x sec squared x dx, hopefully that makes a bit more sense, because now we can compare them exactly. So if we consider this to be this, then we can consider this. So u is x, v is tan x, so it's x multiplied by tan x. We then subtract the integral of u dash is 1, and v is tan x. 1 multiplied by tan x is just tan x dx. So you see how that works? The fact that I chose x to be u, when we derive it we get 1. 1 times tan x is just tan x, so we have one less thing to worry about. Okay, so now we've got that. Let's see. Now we've got the equation, we can finish it or find the answer. X tan x, no problem there, we just leave it. Subtract the integral of tan x. Well, the integral of tan x is negative natural log cos x plus c. So that's what we're going to put in. Negative the natural log cos x plus c. Why? I'm not going to explain here, but tan x equals negative natural log cos x. It's just the way it is. Okay, so now that we have this, let's simplify it down. X stays the same. It's still multiplied to tan x. This side of the subtraction sign stays the same. But think of it as being a negative 1 multiplied. I'm expanding the brackets, but I'm expanding it with a negative. So I'm multiplying a negative onto this and a negative onto this. See, I have to do that before I can get rid of the brackets. It's just like how, I might be overcomplicating it, but just how you multiply negatives by negatives, you get a positive, and a negative by a positive, you get a negative. So I'm multiplying a negative onto negative ln of cos, so I get a positive ln of cos x. And then I'm multiplying the negative onto the plus c, so I get a negative c, because a negative times a positive is a negative. You see how that works? I'm expanding the brackets with the subtraction. Okay, so now that I've done that, we're almost done. You can leave it, well, if you want to, you're done now, but I'm almost done. You can leave it as negative c, but in another video I explained that I like to do things like this, where I'll make h equal negative c. So when I write it out and make it look all neat and nice, I end up with a positive constant. Now I can't make it a plus c because it's not. So I make h equal to negative c, therefore h equals this, therefore we have h. Now if that confuses you, pretend like you didn't hear that and just put the negative c, but if you want to do things exactly, or if you want to be a bit more accurate, then this is, or you want to be neater, this is probably a good way to go. It's just how I do it. Anyway, I'm going to go on to the next example. I'll show you another trick that comes up in this example with integrating as well. Okay, so we got our example 2, dy dx equals cos x 2x plus 3. So we've got our first function and our second function, and they're being multiplied together. Okay, now if we find the integral of dy dx, we just get y, and if we find the integral of all this, we get this. Now some people, and the dx, can't forget that. Some people like to think, well, the equation shows u at first and v dash to be second. So it's much easier for me to make cos x u and 2x plus 3 v dash. But think about it. Just like before when I said you want u to be the one that, when derived, simplifies. Cos, if you derive that, you would get negative sign. If you derive this, you get 2. Which is more simplified? Negative sign is actually making it bigger, so it's not really, it's just changing it. It's not changing it, not in a good way. It's not simplifying it. When you derive this, it's simplified. Some people think that's the only way you can write it. If you wanted to, you could write it like v dash multiplied by u dx. It's still the same thing. They're exactly the same thing. So, just like that, you can rearrange these if you want to. So let's rearrange it. We have y equals integral of 2x plus 3 multiplied onto cos x dx. Now that looks a little, it looks a little better to someone who doesn't really, is not 100% on the topic. Because if you rearrange it like that, then you can see, okay, well I can make this u just like here, and I can make this v dash just like here. My videos aren't there to, if you already know this and you're getting confused, don't worry about it. I'm just going through this to make sure that people understand that just because something is arranged like this doesn't mean it can't be arranged like this. They're both multiplied together. This is just a way that someone's written it. You can flip it around. You just can't put them over top of each other because that'd be dividing. Anyway, so we've got this. We're going to call this u and this v dash. That's been established. Now that we've got that out of the way, we're going to write down, we're going to write down on a separate piece of paper our u's, our u dash, our v, and our v dash. We've said u is 2x plus 3, 2x plus 3, and we've said v dash is cos x. Now what do? Well, now we derive 2x plus 3, we get 2, and we find the integral of cos x, which is sine x, just sine x, because if you derive sine x, you get cos x. That's how you know it's true. Okay. Now's the part where we basically fill in this equation. Okay, I'll try and keep this equation at the top so you can try and follow along. Okay, what did we start with? We started with 2x plus 3 cos x dx. This, if we're assuming that this is this, then we can do the rest. So u multiplied by v, that's u, 2x plus 3, multiplied by v, which is sine x. Now what we're going to do is subtract. I'm going to bring it down here because I'm running out of room, but subtract the integral of v dash, which is of u dash, which is 2, multiplied by v, which is sine x, multiplied by sine x dx. Now what? Well, first of all, this stays the same, this doesn't change, this is fine, but we need to work on this bit. Because as a rule, and it's multiplication by constants, and that means that if we have a constant multiplied to like the function or the variable inside an integral, we can actually bring it out. It's still multiplied, but we bring it outside the integration symbol or the integrand. We bring it on the left side of this funny looking s. So I'll just rewrite this half. 2x plus 3 sine x. Subtract 2 integrand sine x dx. See what I did there? Because there's a rule that says we can do that. If there's just a constant multiplied onto this, the constant's still by itself, it's just multiplied onto this, and therefore it's still multiplied. We'll multiply it later, but the rule states that we bring the constant out in front. Okay, now that we have that, we got to find the integral of sine x. 2x plus 3 sine x minus 2 bracket. Okay, the integral of sine x is negative cos x plus c. Think of it this way, if you derive this, you would get that. Okay. Now, just like in the other question where we had a subtraction and we expanded it out, this might be easy to understand because there's essentially a negative 2. So we're going to expand the negative 2 into it. And it will look like this. I'll just write the first bit. Negative 2 multiplied by negative cos. Positive 2 cos x. Negative 2 multiplied by positive c. Negative 2c. This is why I like to use letters like h and whatnot. So, because I used h in another example for negative c, let's change it. Because we've got negative 2c, let's say, I don't know, let's say w. W equals negative 2c. I am stating that. Therefore, I can write it like this. Equals 2x plus 3 multiplied by sine x plus 2 cos x plus w. I can say plus w because we know w is equal to negative 2c, which is this bit. So that is the same as that there because of this. And if we rewrite what we started with, integral 2x plus 3 cos x, if I can fit it in, dx, I can't fit it in, but hopefully you get it, this is equal to this. So the integral of 2x plus 3 multiplied by cos x equals this. I'm not going to read that out, but you can see that. We just worked it out. Now, thank you for watching. I hope you learnt something. I hope you have a good day.